Okay, welcome back. So last time we talked about a method for solving with sparse triangular matrices in parallel, and that method was using something called partitioned inverses. And today the topic is to talk about a different kind of preconditioner. We talked about incomplete factorizations before. They're very effective, but they have these triangular solves which we saw was difficult to parallelize, even using level scheduling and even using partitioned inverses. We're going to talk about another preconditioner today that is based on approximating the inverse of the matrix directly with a sparse matrix. Okay? And interestingly, this is kind of related to the partitioned inverses because we're trying to represent something, we're trying to represent the inverse, approximate the inverse of a matrix. Actually, partition inverses don't approximate the inverse. They represent the inverse exactly. But here we're going to try to approximate the inverse with a sparse matrix. So these are very well-known preconditioners. They're implemented in a number of packages. I think maybe PETC implements this, or it's accessed. PETC can access some of these sparse approximate inverse preconditioners through some other libraries. So these are also starting to, well, they actually have been, there has been a lot of interest in these methods for many years because of how parallel they are. Okay? So let me explain that in more detail. Okay, so if we're given a matrix A, let's say non-singular A, okay, we're going to try to find a matrix M. Okay, so find a matrix M that approximates the inverse of A, okay, such that M is sparse. And to be precise, we can define a sparsity pattern S, just like we did for incomplete factorizations. We can define a sparsity pattern S, which is the set of locations ij such that Mij, the ijth entry of M, can be non-zero. Okay, so this is useful as a preconditioner, as a parallel preconditioner. Mainly because applying the preconditioner is just multiplying by the sparse matrix M, which is highly parallel. So it's just a sparse matrix vector product. And we talked a lot about this before. And again, you can see how important it is to have an efficient sparse matrix vector product. Highly parallel because you can compute generally each component of the results independently. Okay, so there are many ways of computing sparse approximate inverses, and in this lecture I'll show you some of these ways. And there are methods that try to, there are two large classes of methods that try to choose the sparsity pattern S beforehand, and methods that try to choose it dynamically during the computation of the approximate inverse. So this is a little bit like incomplete factorizations that we saw before, two large classes of methods. So first class, I'll call that static pattern. we're going to choose S beforehand. Sometimes we call that choose S a priori. And then dynamic pattern so here S is adjusted dynamically. During the computation of M. The methods for changing the pattern dynamically are more expensive than the methods for choosing based on choosing the pattern beforehand. Okay, but if you have no idea how to choose the pattern beforehand, then you'll have to use these dynamic pattern schemes. Okay, and usually the static pattern is based on the structure of the matrix A. Okay, sometimes you could take into account its values. And for a lot of problems, like a lot of simple problems, like just simple diffusion problems, discretization of diffusion problems, then choosing a static pattern is fine. Okay? And in many PDE problems, choosing a static pattern is fine. But for other problems, we don't know how to choose a static pattern, and we have to use these dynamic schemes. In this lecture, I will concentrate mostly on just assuming that we know a static pattern, and then how do we compute M? Okay, so we'll start with a method that I will call the diagonal block method. I think this is the very first sparse approximate inverse method. It was described in 1973 in someone's master's thesis. So it's quite impressive master's thesis, in fact. But a paper didn't appear on this until much later, I think 1983. This master's thesis was 1973, so maybe about 10 years later there was a paper. So this was Benson, 1973 master's thesis. His advisor was Paul Fredrickson, and later on they wrote a paper. And the idea is that given S, so we have a matrix A, and we're going to, given S, the sparsity pattern, we're going to find an M such that A times M, okay, if M is the exact inverse, then A times M is the identity matrix, right? But we're going to only look at the ij locations in AM, and we want those to match the ij locations in the identity matrix, okay? For ij belonging to the sparsity pattern. Okay? So we're not going to ask for every single location to match. If we did, we'd be computing the exact inverse. Okay? Here we're only going to ask for this to match in a small set of locations, right? And this S, again, is also the sparsity pattern of M. Okay? This, to find what M is, the problem actually decouples into independent subproblems. Okay? This problem, in other words, to compute M, decouples into n independent subproblems. One for each column of M. Okay? In other words, you can compute the sparse approximate inverse in parallel, let's say one process for each column. So not only can you apply the approximate inverse by multiplying by m, computing m is also very parallel. Okay, so to see what these subproblems are, for column J, so we're just going to look at column J of this first equation, AMJ, where MJ is the jth column of M, okay? And subscript I, the ith entry of that column, okay, is equal to EJ, which is the jth column of the identity matrix, or the jth unit vector, and the ith entry of that, IJ belonging to the sparsity pattern. So this is what you need to compute for each individual column. So M itself can be computed in parallel. So it seems very attractive. This is, I think, one of the reasons why people were interested in this for parallel computing. Each one of these is going to involve solving a small linear system, which I'll write down explicitly in a moment. Let's call it M by M. M is going to be much smaller than N. Linear system. Actually, I shouldn't say each, because M is going to be equal to the number of non-zeros in column J. So it will be a different size for each column. So let me not say each over here. So the subproblem involves solving an M by M linear system where M is the number of non-zeros in the column J that you're trying to compute. Okay, so let's look at an example. And let's just use this simple 4x4 tridiagonal matrix. Okay. And let's say that we're interested in the second column, so J is equal to 2. Okay. So I'm writing down, that's A, and now this is MJ. And let's suppose that the pattern that we want is this one. Okay, so S is the set of allowed non-zeros, and 2 of the non-zeros that we're going to allow is 2, 2, and 3, 2. Okay. So in the second column, we're going to allow these 2 non-zeros. So that's MJ. And then EJ second coordinate vector. Okay, so A is known, right-hand side is known, and we want to compute these 2 things. Okay. You'll notice that because of the zeros over here, the first column and the second column don't matter. And because we want to have equations for ij is equal to ij is in the sparsity pattern, we only need the second and the third equations. The first and the last equations don't matter. Okay? So this simplifies to looking at where these four x's are these four values here. Okay? So these four x's is, in this example, is just a diagonal block of A, okay, which is why the method is called the diagonal block method. And if the matrix A is symmetric positive definite, then all of these blocks are going to be symmetric positive definite because these are just principal submatrices of A, or principal submatrices of permutations of A in general. Okay? So these matrices are guaranteed to be non-singular. So there's no question of whether or not you can solve with these small submatrices. So in this example, we need to solve with diagonal blocks of A. If A is SPD, then the diagonal blocks are SPD. So that's nice. Another observation is that in general, when we compute all of the entries in M, we might not use all of the entries in A. Okay, it depends on how you choose the sparsity pattern. So that could be good or bad. One way to see this is that suppose that A is dense, okay, and you choose some sparsity patterns. Let's say this one, something simple like this for each of the columns. You'll see that you don't use all of the entries in A. So that could be good or bad because sometimes, so bad meaning, well, if you're not using all of the information, right? So maybe the method is not so good because you're not using all of the information. But good maybe because sometimes you have a problem that is very dense. Okay, suppose you have a dense problem that comes from a boundary element problem, for instance, and you want to compute a sparse approximation to it. You can do that relatively cheaply, assuming that the values that you're not using are going to be fairly small. Okay? So not all elements, not all non-zeros in A are needed to compute M in general. And this could be, as I said, good or bad. So some questions about this method. One question is the M that we compute guaranteed to be non-singular? We would like M to be non-singular because we're computing an approximate inverse of a non-singular matrix, and the preconditioner has to be non-singular, otherwise we're going to run into difficulties in our iterative method. So one question is M always non-singular? And another question, kind of related, if A is symmetric and positive definite, will M also be symmetric and positive definite? If A is symmetric and positive definite, then we would like to use the conjugate gradient method. And for the conjugate gradient method, we also require a preconditioner that is symmetric and positive definite. Okay, so we would like M to be SPD. So we have these two questions. Unfortunately, the answer to both these questions is no. So we're not guaranteed, depending on how we choose the sparsity pattern and the matrix for the matrix, we're not guaranteed that the matrix is always non-singular. And similarly, we're not guaranteed that M will be SPD. Okay, so these are kind of unfortunate results for this method, which makes you think, well, if you have a non-symmetric problem, then maybe you would try this. If you had a symmetric problem, then maybe this is not going to be as effective as something else. Okay, so that's the diagonal block method. Let me now talk about another method called the least squares sparse approximate inverse. Okay, so here we're given S again, and we want to find M such that, so instead of this condition, we're going to have a slightly different condition. The condition is that M minimizes I minus A times M in the Frobenius norm. Okay, so if M is the exact inverse, then this quantity is 0 and the minimum is 0. Okay, but it's too expensive to compute the exact inverse. So we're going to try to do this minimization given that M is sparse. So given some sparsity pattern for M. Okay, and this problem also decouples into independent subproblems, this time independent least squares problems, because you can write this as the minimization, the sum I equals 1 to n columns of Ej, where Ej is a jth column of the identity matrix, minus A times Mj, just like before. Okay, so instead of writing the Frobenius norm, it's a vector, so I'm going to write this as the 2 norm. So this is just a least squares problem. Right, we have n least squares problems to solve. So again, the computation decouples into independent subproblems. So to be clear, these are least squares problems. So let's do an example. I'm going to choose the same matrix, but I'm going to choose a slightly different sparsity pattern. Okay, and let's choose J equals 2 like we had before. So we want to minimize, so this is for the second column. Okay, so we want to minimize okay, so that is the second coordinate vector. It's going to be the same matrix as before. It's that tridiagonal matrix. And we're going to need M. And instead of this pattern, I'm going to choose a slightly different pattern to make the problem a little bit more interesting. Okay, so we want to minimize this. So the vector is known, the matrix is known, and we want to minimize this. Minimize this to find these two values of x. And like before, because we have two zeros over here, the last two columns of the matrix doesn't matter. Okay? So this also simplifies minimize 0, 1, 0 minus where this least squares matrix is 3 by 2, so it's not square, that's why it's a least squares problem, is from this part of the matrix. And you can see that the least squares problem will be bigger if we have sparsity pattern that is bigger. So number of non-zeros is, in M is large. Yeah. Sorry? M2. Why is this? Yeah. That's because I chose it that way. So we choose that beforehand. This is prescribed by S. Right? So over here I chose S to be like this. And here I chose S to be a little bit different. I could choose these two, right? Like before. And in that case, the least squares matrix will be this. And when I was writing the notes, I decided I didn't like that because that means every single column is involved, right? And I wanted to show that in general, these least squares problems can be shorter. Okay, so that's why I changed it a little bit. But I see it caused some confusion. Okay, but in any case, these are small least squares problems, right? If for instance, we have only 2 non-zeros in each column of M, then the least squares problems will all have 2 columns, right? 2 columns selected from the matrix A, right? And it will only involve a certain number of rows for which there are non-zeros in those 2 columns. So they're small least squares problems. Let me point out that the least squares problems are full rank if the matrix A is non-singular. Okay. And we can ask the same 2 questions as before. M computed this way, is it always non-singular? And if we have a matrix A that is symmetric, will M also be symmetric? Unfortunately, the answers to those two questions again is negative, so no. So not always non-singular and not always symmetric. We'll see another method later on that gets around those two difficulties. So again, if A is symmetric, M will not be symmetric in general. If you have a non-symmetric problem, then the symmetry is not going to be so much of an issue. Okay? So let me talk now about a generalization of these two methods. And this is due to Kołtolina and Yerman. (1986), husband and wife team. Okay, and I'm going to use their notation. So in case you read their papers, you can match these notes with those papers. So their notation is very similar, except that they're going to compute a left approximate inverse. So they're going to do MA rather than AM. So if you're going to use left preconditioning, you can compute that instead. I generally like to use right preconditioning for various reasons. You could also see that I minus MA is fine as well. And the other difference in notation is instead of calling it M, they call it G. Okay, so you can think of G as the left approximate inverse. So here in this generalization, so given some sparsity pattern S, we're going to find G by minimizing this functional that I'm going to call FW. Okay. And that's very similar to what we wrote down before. Okay, but instead of the Frobenius norm, we're going to use the W norm. Okay. Where W is symmetric and positive. W is a symmetric and positive definite weight matrix. And this is just defined, this latter thing is just defined to be the trace of I minus GA times W times I minus GA all transposed. Okay. And if you've forgotten some properties of traces, the trace of, let me write this instead, the Frobenius norm squared of some matrix, let's call it B, is equal to the trace of B transpose B. Okay, so the trace, you may recall, is just the sum of the diagonal entries of a matrix. Okay? And if you want to compute the Frobenius norm of a matrix, you can take this outer product. Okay, so that makes a sum onto the diagonal that involves some of the entries that you need for the Frobenius norm, right? So this weighted norm over here is related. There's just this weight matrix in between. Okay, and if the weight matrix is just the identity matrix, then it's just the regular Frobenius norm. Okay, so there's nothing really too special about that line. So maybe we'll write observe if the weight matrix is the identity, then we have the Frobenius norm. Okay. So this seems like a good thing that we want to do, right? This is something that we want to minimize, but the generalization is that we're going to use this weight matrix. Okay? And if we want to minimize something, over here we wanted to minimize something, and we found that we just had to solve least squares problems. But in general, if you want to minimize something, you can just take the partial derivative with respect to each of the things that you want to optimize. In this case, they are the entries in G. So take the partial derivative and set them equal to 0. So the partial derivative with respect to these entries in G, okay, of the function of the objective, and we're going to set that equal to 0, and this is for all ij in the sparsity pattern. And you can write out this matrix. You can write out this matrix and then take all the derivatives. It's a little bit tedious if you're not familiar with that, with certain rules on how to do that. But it easily leads to the following condition. G, A, W, A transpose, ij. The ijth entry of this product is equal to WA transpose ij for ij in the sparsity pattern. Okay, so if you set all of these partial derivatives to 0, you get exactly this in matrix form. Okay? And it looks a little bit like what we saw before, but we'll see how it looks more like what we saw before. The optimal value at the minimum, the optimal value of the function f, let's say f w of g, the optimal value is the trace of w minus the trace of g a w. Okay. We'll try to show why this is the optimal value. So to see why this is the optimal value, fw of g, Okay, so FW of G is this, right? I'm just going to expand out the quantity inside the braces. So that's the trace of W, okay, plus 2 times the trace of GAW. Okay, so there's a term in here that's GAW. Actually, this is a minus, I guess. So there's a term in here, GAW, and there's also a term here, W, A transpose, G transpose, but the traces of those two things is the same. So that's why we have 2 times the trace of that. Plus the most complicated term, which is this outside term, plus the trace of G, A, W, A transpose, G transpose. Okay. So this is what that is. Now, in order to see what the optimal value of this is, we have to utilize something that led to the optimal value. So we're going to utilize this fact. So we have to utilize this. And you can see that we're going to utilize this GAWA transpose appears over here, GAWA transpose. Okay, but we're going to be interested in the trace of this thing times that. Okay, so the argument here is a little bit tricky. So let's look at this second term. The second term is the trace of some matrix, that's this matrix, times another matrix, which is G transpose. Okay? And G is sparse. By definition, this is the sparsity pattern of G. Okay? And we're interested in the diagonal of this product. Okay? And if we think about computing the diagonal of this product, not all of the entries in this matrix are needed. Okay, we only need the entries of this matrix, this first matrix, that will multiply non-zero values in G transpose. Okay, and those values that we will need is exactly the sparsity pattern of S. Okay, so we only need the ij entries in here, the ji entries over here, because those are the ones that will multiply together. So we only care about the diagonal of the product. In this first term. So we only care about these guys. So we can write this second term as the trace let me write, we're going to substitute this. Okay, so we can write the second term as the trace of, that's WA transpose, and that's G transpose. Okay. WA transpose G transpose is just the transpose of this if W is symmetric, which I said that W is going to be symmetric. So these two traces are the same. So the final value over here, the final optimal value is the trace of W. So we're going to cancel out one of these over here, minus the trace of GAW. Okay. So now let's look at what we have when we choose W in different ways. If W is equal to A transpose, not A transpose, A inverse transpose. Okay, so we put W equals A inverse transpose. Then this goes away, right? And this goes away. So we have GA IJ is equal to the identity IJ for IJ in S. So this just looks like the diagonal block method. So the diagonal block method is this general method with a choice of weight matrix being A inverse transpose. And the optimal value of FW is equal to the trace of A inverse transpose minus the trace of GA A inverse transpose. There's a further simplification if we assume that A is symmetric. So further, if A is symmetric, you can see that the optimal value is the trace of, let's say, A inverse minus the trace of G. So here the A inverse goes away. And this gives us a little bit of a hint on how to choose a sparsity pattern. We want to choose a sparsity pattern that will maximize the trace of G. So we can't do anything about this term, right? But we can try to make this as large as possible to make the objective as small as possible. So we could choose S to maximize the trace of G. Okay, so this is like the diagonal block method. It is the diagonal block method when A is symmetric and positive definite. Okay, so that's one choice of W. Another choice of W is just the identity matrix. And you can maybe see immediately what that leads to. So we know that if it's the identity matrix, then that's just the Frobenius norm. This is obviously just the least squares approximate inverse. which I just erased over here. But if we write it out, we have G A transpose I jth entry is equal to A transpose I jth entry for ij in S. Okay, so in other words, I've taken this and I've substituted in the identity matrix for W, G A transpose, A transpose. And this is an interesting way to view the least squares method, because this is just solving the least squares problems using the normal equations. Okay, so we have a A transpose. It's actually, it's the normal equations on the other side, right? Because now we have this left approximate inverse. So this is like this is basically formally expressing the solution as the normal equation solution. It has the optimal value of f is equal to n, which is just the trace of the identity matrix minus the trace of GA. So this is a view as solving the normal equations. So one other choice, if W is equal to, this is maybe a little bit of a weird choice, a very interesting choice though, A transpose A inverse, then, so substitute that W into the general expression we had before. Okay, so substitute that into there. Then we have Gij is equal to A inverse Ij for Ij in the sparsity pattern. Okay? That means that in our sparse approximate inverse, all of the entries in the approximate inverse are exactly equal to the entries in the exact inverse on the sparsity pattern. Okay? It seems like an ideal thing to have. Unfortunately, this isn't a practical method because there's no cheap way of computing G using this weight matrix. So not practical. Since we don't know how to compute it, we don't know how to compute it cheaply. And for completeness, the optimal FW is equal to the trace of A inverse minus G. Okay, if we had the exact inverse, that trace would be 0, times A inverse transpose. Okay, so these are three choices, and you can see that they lead to three different kinds of approximate inverses for different weight matrices W. So let me say something about non-singularity. So I'll just list some results that are known, right? So we're interested in what can be known if the optimal value is small enough. Okay? So if I minus GA in this W norm is less than 1, okay, then we can say three things. One is that GA is non-singular. Okay. The second, we can say something about the condition number of GA. So GA is the precondition matrix, right? So we want the condition number of that matrix to be small. So the condition number of GA, and let's say the 2 norm condition number, that's equal to 1 plus epsilon. I haven't defined epsilon. So let's say that this is epsilon, less than 1. So this norm is epsilon, 1 plus epsilon over 1 minus epsilon. And then C, GA is positive definite. Which in the general case means that the eigenvalues of GA are all in the right half plane. Okay? Something I want to note, however, is that this condition that the norm is less than 1 might be difficult to attain, meaning you might, for your matrix, need a relatively dense S, meaning a lot of entries in S, for you to be able to achieve this. But in practice, you often get perfectly fine preconditioners when you don't have this satisfied. Okay, you could still have something that is non-singular even if that is not satisfied. So in practice, this condition may be expensive to obtain. Okay. Let me now talk about something called factorized forms of the sparse approximate inverse. And these factorized forms of the sparse approximate inverse have many advantages, especially if your problem is symmetric and positive definite. You can guarantee that you have a preconditioner that is also symmetric and positive definite. And this is also due to Koletelina and Yerman. So given matrix A, now we're going to find a G with sparsity pattern S such that G transpose G is approximately equal to A inverse. So what we had before was some matrix M, or maybe some matrix G, that approximates A inverse. But now we're going to try to find a product of two matrices, actually not necessarily the same, okay, that approximates the inverse. Okay, so this is in factored form. So this is why this is called a factorized sparse approximate inverse. So as I said, that there are advantages of this form. First is if A is symmetric and positive definite, then we can guarantee that G transpose G is symmetric and positive definite. Okay. So we can use this as a preconditioner for the conjugate gradient method. And another advantage is that G transpose G tends to be denser, more non-zeros than G, meaning there's the possibility that G transpose G can approximate the matrix A, which for PDE problems is going to be dense, better than a single sparse matrix. So the factorized this factorized product might be able to approximate A inverse better than just a single matrix. So what I'm going to describe, we will choose G as lower triangular. You can imagine that, well, we don't have to choose G as triangular, but all known methods for factorized sparse approximate inverses choose G as lower triangular. Yeah.
This method is better for unsymmetric matrix A.
Yeah, so I could have written G times H for some non-symmetric problem in general, right? And but normally the main advantage comes from this. So if matrix is symmetric, positive definite, then I can guarantee something that is symmetric positive definite. So let me, if you'd like, you can change this in your notes to G times H. When I wrote the notes, I was a little bit, I didn't know where I was going when I was writing the notes, right? So I didn't know I was going to try to be more general over here and then be more specific. So this is the more specific case. Does that answer your question? Yeah? So we're going to choose G as lower triangular. So I've actually spent some time trying to figure out how to trying to invent some sparse approximate inverses in factorized form that are not triangular. And you can try to experiment with that and see if you can get some things that are better. But the results are not very conclusive. But all of the methods that are known, so all known methods for computing these factorized sparse approximate inverses use G as being triangular. So if G is lower triangular, then G approximates the lower triangular Cholesky factor of A. So if A is symmetric and positive definite, G approximates the Cholesky factor, which we can call L. Okay, so A equals L transpose. That's the Cholesky factorization. And if we take the inverses on both sides, A inverse equals L inverse transpose L inverse. Okay? And that's equal to, approximately equal to G transpose G, okay, which is what we're seeking. So G is approximately the blah, blah, blah. I should say an inverse. G approximates the inverse of the Kleski factor of L. That makes sense. G doesn't approximate the Kleski factor. It approximates the inverse of the Kleski factor. Okay? So how are we going to compute G? And in particular, we don't know what L is. We don't want to compute the Kleski factor to compute G. Okay? And you'll see that this method is quite remarkable in that you don't need the Kleski factor to compute G, even though we're going to start by saying we're going to minimize I minus G times L, say in the Frobenius norm. Right? So we want G to approximate the inverse of L, but we don't know what L is. This is kind of a weird problem. We don't know L. But to solve this least squares problem, I think I may have erased it already. Did I? No. So I haven't erased it yet. We need to solve that, right? So let's write that down. So that's G times A, in this case, is our L. So L transpose Ij is equal to L transpose Ij for Ij in S. Okay, so this is something really remarkable. We have L transpose in here, and that's just A. And we have L transpose in here. So this thing is, well, do we need the Kleski factor after all? But this S is a lower triangular sparsity pattern, right? Because it's a sparsity pattern of G. It's the lower triangular sparsity pattern of an upper triangular matrix, L transpose. So we don't need to know all of L, we just need to know the diagonal of L. So this is the lower triangular sparsity pattern of an upper triangular matrix. Therefore, only need the diagonal of L. Okay, so we need less and less of the Kleski factor. We don't know the diagonal of L either. Okay, but we're going to do something to try to get around that problem as well. So in particular, let's note, this is a lower triangular pattern. So we can't really solve this problem because we don't know the diagonal of L. What we're going to do instead is we're going to solve for, instead of solving for G, we're going to solve for G tilde. Okay, where G tilde is a diagonal matrix times G. G is what we really want. Okay, but we don't know the diagonal of L. So we're going to solve for a scaled version of G. So D is a diagonal matrix. Okay. So we'll solve instead G tilde times A, I jth entry is equal to the identity I jth entry, ij belonging to S. Okay. So we're just going to assume here that the diagonal is the identity matrix, but we're going to solve for a scaled version of G. So we can find that G, right, using independent subproblems. It's like the diagonal block method applied to, in this case, right? And then after that, we find D such that G tilde A G tilde is approximately equal to the identity matrix. So back over here, if we left multiply by the inverse of L and right multiply by the inverse of L transpose, that's going to be equal to the identity matrix, right? So that means that G times A G transpose is approximately equal to the identity matrix. Okay? Actually, this is not G. These are, that's not tildes. Okay, so we want GAG is approximately equal to the identity matrix. And G is equal to D inverse G tilde. Okay. This inner matrix can be computed, at least the diagonal of that inner matrix can be computed easily. And all we need to do is to find the D that scales the diagonal of this matrix to be the identity. So the diagonal of D inverse G tilde A G tilde transpose D inverse is equal to the diagonal of the identity. Okay? So this gives us D, and from having D we can have G. Okay, so in the last minute, let me give you an exercise, a simple exercise to try for next class. And that is just to compute the least squares approximate inverse of this matrix, this tridiagonal matrix, our favorite tridiagonal matrix. Let's say 7 by 7. Let's call that A. Using a sparsity pattern S, which is equal to the sparsity pattern of the original matrix A. Okay. And what I suggest, because you have to solve a lot of least squares problems, just use MATLAB to solve all the least squares problems. Or you could write a MATLAB program to compute it directly. Okay? And then I think just doing it once will show you some interesting things about what the approximate inverse of this matrix looks like. Any questions?
Can we impose some constraints to the least square problem? and then we can ensure that.
Yeah, so people have done that, in fact. There are certain properties that we might want in the approximate inverse. I think you're probably asking about something more general, which is you want to enforce some non-singularity of the result and things like that. Those are kind of hard to do, but people have tried to enforce other types of conditions that will make them think that they might have a better approximate inverse. One example is that, let's say that we have the matrix A and we have the matrix M. We want A times some vector E to be exactly equal to M times some vector E, where E might be the vector of all ones, because you know that you want your preconditioner to be accurate on that subspace, on a certain subspace. So people have done things like that. So this would be an additional condition to try to satisfy, which you can add to the least squares problems. But additional conditions to satisfy symmetry or non-singularity, that I think is very hard. Okay, see you next class.